Hi everyone, Miss Milender here. And so before we get into the actual math of dimensional analysis, let's talk about SigFigs for a few minutes. So how do you use SigFigs in this? Well, dimensional analysis is all multiplication and division. So that's the only rule you have to worry about during dimensional analysis. So it's the rounding to the least number of SigFigs that you have in your original number. The problem is sometimes numbers in equivalence statements and conversion factors count and sometimes they don't. We're going to talk about that. Okay, where did SigFigs come from in the first place? Well, they came from the reading of instruments and the first best guess and the uncertainty and all that. So if a number is read from an instrument by you or somebody else, it still counts as a SigFig. The problem comes in when you're talking about numbers that were never read from an instrument. Those don't count as SigFigs. So let's go over 4 things you need to know to determine whether or not a number is considered a SigFig. So we call these numbers pure numbers. If there's no uncertainty, there's no first best guess, then they're called pure numbers. So let's look at some examples of pure numbers. If you look at the equivalence statements over on the right, you can see that they have something in common. If a number is true by definition, which means it's in the same measuring system, then they're considered pure numbers. Because yeah, ultimately somebody had to measure these at some point, but now they're just accepted, they're true, they're by definition. So we have examples in the metric system, 1,000 meters in a kilometer. In the standard system, a mile equals 5,280 feet. And then time is always a pure number because by definition there are 3,600 seconds in an hour. So the second way to tell if a number is a pure number is whether or not it's a power of 10. If you have a power of 10, then it doesn't count as a SigFig. In the first top 2 examples, the reason those don't count is, yes, they're all powers of 10, but they're also from the same system. So a gram and a kilogram are both metric numbers, so those wouldn't count as SigFigs anyway. But if you get down to the next 2, you have 0.3937 inches being compared to 10 millimeters. So 10 millimeters acts as the known, and what you're comparing to it is this 0.3937. If you look over at that 0.2642 gallons, it's the same kind of thing. You're comparing a gallon or a portion of a gallon to 1,000 milliliters. And then the final one is you're comparing a kilometer to the size of a known mile. So the power of 10 kind of acts like the known. Powers of 10 in equivalence statements are pure numbers. There they are. So I've circled all the powers of 10. So the next way you can tell if it's a pure number is whether or not it's counted. So if the number's small enough, we can assume that your counting is accurate and therefore there's no uncertainty and therefore there are no SigFigs. Apples to a gross, a class to 20 students, 8 students make up 2 teams. Those can be counted and we can assume that you didn't make any mistakes. So counted numbers aren't SigFigs. And last but not least, if a number is given as part of a formula. So if you look below, you can see in the 2ke, the 2 doesn't count, 4/3 pi r cubed, and the average calculation with the 4. So those just come as part of the formula. They do not count as SigFigs. That is everything you need to know about SigFigs and dimensional analysis. Thanks for listening.